We'll be covering a short section of Chapter 12 in the Scholar textbook, and in particular we'll be covering Section 12.2 under these pages, and we'll be discussing pseudo-noise sequences. So the reason we examine these pseudo-noise sequences is to understand how experimentally we would estimate the bit error rate. In fact, this is going to be part of an assignment looking at equalization. You want to know whether the equalization has improved your bit error rate, so you must first estimate the bit error rate and then see if it has improved after equalization. So we've done something similar with an Monte Carlo estimation of BER, but previously it was always in MATLAB simulations, not in the experimental. So what would we do in MATLAB? We would generate bits, we would simulate the system, and then we would count errors. Experimentally, we do the same thing. Generate bits, pass through a real experimental system, and record the data, make a detection, and make errors, and count the errors. So in that case, they're the same. So in all cases, we're exploiting the fact that we know what the data was sent. So if we know which bits were sent, we see which bits we receive, and we see if they've been flipped. And so then we could use the same techniques of estimating the Monte Carlo. But there are some things that are different. In MATLAB, you have perfect synchronization. You know exactly when the data starts, when it ends. You're a lot more omniscient in MATLAB. How do we actually do the synchronization in an experimental setup? And that's the challenge that we face and why we use these pseudo-noise sequences. So when we think about what's different, another difference between the MATLAB simulation and the experimental is that in MATLAB we take a block of data, we push it through our system simulator, and then we take the output block and we compare it. It's kind of like one frame at a time. But in the experimental data, that's not how it works. In the experimental data, there's this cycle of continuously sending the same block of data. And why is that? Because when we receive it, we don't know, when we're going to receive it. So we have this continuous transmission of data, and there's a couple reasons. We could have used framing, but that really doesn't, that might help a little bit, but in the end, it doesn't help enough because the synchronization problem is quite precise. I have to get it synchronized within 1 bit on the beginning. So how do we do this synchronization? Well, we need some special properties in our data to be able to do some really good synchronization. And let's see what those special properties are. Well, we're going to talk about data. Is it really random? Well, it's not random because I generate it and then I transmit it and I know what I transmitted. And in MATLAB, I do use the random command. I say generate a new one every time. But that would not be an effective way to do it experimentally. It would make synchronization very difficult to have truly random data. So instead what we do is we use a sequence which is pseudo-random. Pseudo, so that's why we get the pseudo. And we'll be talking about the name, why we're talking, there's 2 names that are applied to the same sequences. One of them is pseudo-noise and one of them is pseudo-random. So let's see where these vocabulary comes from and how we use these sequences and what are the characteristics that are so important in these sequences. Well, the first important characteristic of a pseudo-noise sequence is balance. It's a sequence of 1s and 0s, right? So if I gave you a sequence and they were all 1s, well, it wouldn't look much like noise and it wouldn't look very random. They would all be the same. So one of the properties of a good pseudo-noise sequence is that the number of 1s and the number of 0s is the same. They're about half and half. Makes sense? So it looks random even if it's not. That's why we get the pseudo. That's why we say pseudo-random. Now, another important characteristic is that there are no long subsequences of all the same number. So, in other words, I could have half 1s and half 0, but if I put all the 1s together and all the 0s together, well, that doesn't seem very random, doesn't seem very noise-like. So, we talk about subsequences, and the length of the subsequences with all the same bits should not be too many, okay, too frequent. So it should look random, even if it's not. So that's why we call it pseudorandom. So the last criteria is what we call a constrained cross-correlation. I would like the cross-correlation to be as peaked as possible and very small when I'm not exactly synchronized. So this is where it becomes more obvious where we're looking at the synchronization. So what I say when I say constrained is I mean that the correlation of a sequence with a cyclical shift of itself should be very, very small. And when it's exactly lined up, very, very strong. And this is really when we're starting to see why we call it a pseudo-noise sequence. So I said there were two names. The first name is PRBS, a pseudo-random bit sequence. That seems like it matches what we were saying about balance and no long runs of ones or zeros. Now, PN sequence, pseudo-noise, why do we call it pseudo-noise? And it's that third criteria that makes it a pseudo-noise. So let's have a look at why. I'm talking about, if I back up, I said that I want the correlation to be very small when I'm out of sync, right? So what I'm saying is that that's like requiring a delta function. I'm asking for the constrained correlation, so the cross correlation of this signal with itself, which is really the autocorrelation, is something whereas if I have exactly the sequence lined up with itself, boom, I get a big peak. And if I'm a little bit off, no, almost nothing, really, really low. So this is like a delta function. And if we have a delta function in the time domain, what does that mean in the frequency domain? That means that in the frequency domain, whoa, if I could spell frequency, that I have a constant. So in the time domain, when I have a delta function, in the frequency domain, the Fourier transform of that delta function is a constant. And that looks like additive white Gaussian noise. So when it's noisy, noise is random. So it shouldn't be all ones or all zeros. So that's these two criteria. But if it's noise, if it looks like noise, then I should have something that looks like an autocorrelation function of a delta function. And so this is why we have these two names. One that refers really to the first two, and then the thing on the third one, we get why we call it a pseudo-noise function.